Look at this next RSA project. So here we're going to use a somewhat longer key. It's still going to be short, but not as ridiculously short as it was before. So here's the same summary of key generation. So here's the problem statement. Megan's public key is this, which is about a 20-digit number. Find her private key. This is what should not be possible, but it will be possible unless your public key is long enough. And to be long enough, it really has to be 2048 bits now, which is about 3 bits per decimal. That's about 700 digits in base 10. And we're all supposed to be moving to 3072-bit public keys, and those are going to be 1,000 digits long. So this is not long enough at all. It's about 20 digits long. So you install PyCryptodome in your Python, and now you can factor n. Now, one thing you can do is find the square root of it. And there are various possible weaknesses in a public key, and one of them is, I think the flaw here, that the P and Q are near each other. That means they're both near the square root. So that's something to try. There's a bunch of ways you can do it wrong. Another thing you can do is use known public prime numbers instead of finding random ones. There's various flaws you can make in RSA. Well, here what we're going to do is find the square root. So you have the square root number here, and then you just try numbers near the square root. So you take a series of, you start at the square root, and then you move by -2 because you only want odd numbers. Even numbers can never be prime, other than 2. And then you just print I and n% I, because n modulus I will be 0 if I is a multiple of n. And otherwise it won't be 0. So you'll see here, it prints out some numbers, and one of them is 0. So now you've found a prime. It turns out that it was just very close to the within 40 of the square root. So that means P is going to be on one side of the square root, and Q will be about as far on the other side of the square root. And so once you find anything where this calculation gives you 0, you've found one of the prime. This number is P. By tradition, P is the smaller and Q is the larger. And I started from the square root and went down, so I'm going to find P. Q will be on the other side. And so you can get Q by just doing n over P. That'll give you Q. So you see here P is 107.11.409, and Q is 107.11.423. So P is a little bit smaller, Q is a little bit bigger, but they're both pretty close to each other, so they're not hard to guess. So this is a poor choice of P and Q from the viewpoint of cryptography, but now that you have it, you can now calculate FIN, you can calculate the private key. Now, the way we did the private key before, we did a brute force search by just multiplying until we found 1. There's a better way to do it. The library has an inverse function that will find it. And Euler created an algorithm that finds it reasonably fast by a series of successive approximation. So we can just do the inverse of E FIN. It'll just calculate it for us. So we'll get the decryption key, and now you can encrypt and decrypt a message. So this gives you a little bit of practice doing it more. And here's another one where you have a public key, and you don't have P or Q. You're going to have to find them to decrypt it. And so once again, this is not long enough at all to be uncrackable. That's maybe 60 digits long. But I think the same flaw will be here. You'll find that it's relatively close to the square root, although not as close as 40. I think you have to go like tens of thousands away. But it's not too far to get there it's not impossible to get it with Python. Python is pretty fast. So there's some more RSA games to play so you understand how RSA works. That's all I wanted to show you.